Alright, folks. Well, welcome back. Chapter 6. We're opening on up a new discussion on the topic of vectors. So we just finished on up a lot about trigonometry. We're going to be talking about a new concept of vectors, but a lot of relationship and a lot of connection between what we were just talking about with trig for the last two chapters. First and foremost, what is a vector? Simply put, a vector is anything that represents both direction and size. So something that shows movement and has a specific direction and a specific size. So for example, the velocity of a ball that is moving represents a vector. The speed of the ball represents its size, or what we are going to talk about as its magnitude. So to get things kind of rocking as to what a vector is, let's take it to the xy axis. We're talking two-dimensional for a vector here. On the left-hand side, you see a basic point on a coordinate grid, a comma b. Well, a vector just simply represents what does it take to get from one point to the next. So for example, on this right-hand side diagram, if you started at the origin and wanted to get to point B, you would have to go A units to the right and B units up. And so ultimately, that's what a vector is. A vector represents in component form, that's what I'm writing right now, is what's called component form, the number of horizontal movements, either left or right, and the number of vertical movements, either up or down, to get from one point to the other. Now, it does not just have to be the origin. So this is standard representation of a vector, okay? If a vector had a particular name, for example, if it was going from point P to point Q, we would call it vector PQ. We also can reiterate vectors using just single variables that are kind of highlighted, if you will, that usually are using V or U, and it's very hard to draw these. But it's almost a bolded format of a variable as well. Now the magnitude is huge. The magnitude is the size of the vector. And another, it's the length of the blue arrow. That's ultimately what that magnitude represents, is the length of that blue arrow. So let's go real basic and get things started as to how to find a vector. You might remember this from your geometry days. We call it the head minus tail rule. To get from one point to the other, we take the difference between the second x-coordinate and the first x-coordinate, the second y-coordinate and the first y-coordinate. So to go from, and I'm just going to draw this out to get things started for us, to draw this out, 1, 2, 3, 4, 1, 2, here's a point R. It says at negative 4, 2. So there's a point R at negative 4, 2. And it has a vector that goes from R to S at negative 1, 3, 4, 5, 6. So we've got ourselves a vector, vector RS. We would label that guy at RS with the arrow on top. Then we also have a vector PQ, and that vector PQ is at 2, negative 1 for P. And we've got one at Q, 3, 4, 5, and up 3 for Q. And ultimately, what we are trying to identify is that these two vectors are equivalent to each other. Well, we can do this by identifying the head minus tail rule for both of these and making sure that the component form of both of these vectors are exactly the same. So, for example, to find RS, we would simply just take negative 1 minus a negative 4, which is a positive 4, comma, 6 minus 2, and we get a positive 3, 4. So I went 3 units to the right and 4 units up. So for PQ, same thing. Head minus tail. Take 5 minus 2, and 3 minus a negative 1. And once again, you get 3 comma 4. 3 units to the right and 4 units up is how I went from the starting point to the ending point of that vector. Now, this is not the size of the vector. This is just showing that the vectors are equivalent based on their component form. We'll talk about size of a vector next with its magnitude. The magnitude of a vector is just simply the size of a vector. Remember, a vector has two things, direction and size. What we just did represented its direction. What we're going to do now is going to represent its size. So the magnitude, as you can see here, hopefully looks a little familiar to us. Yes, you guessed it. It is the distance formula, okay? This is a direct correlation to the distance formula, but we're going to go ahead and first put it into component form and utilize this second part of the definition of magnitude. Because once you find in a component form, it means you've already taken care of the head minus tail rule, and it just makes our life a little bit easier. So let's go ahead and find the magnitude of PQ. They also say that they want to represent the vector PQ as that bolded variable B. Now, I don't do a good job bolding the variables using, just the screen and stuff like that. So understand that that's not just a plain B, it's a bolded kind of left-hand heavy B there. So it says that P is at negative 3, 4, and Q is at negative 5, 2. So that means head minus tail is negative 5 minus a negative 3, so plus 3, and 2 minus 4. So that means that we've got ourselves a vector in component form of negative 2, negative 2. So basically what that means is 2 to the left, 2 down. So the size of that vector, we're going to call this guy vector V's magnitude. We utilize those absolute value bars to represent that magnitude. And we take negative 2 squared plus negative 2 squared. So we get the square root of 8. And then ultimately we get 2 root 2. So what 2 root 2 represents is the size of the arrow, okay? So the size of the arrow from P to Q, aka the vector V, negative 2, negative 2, has a size, or the real wording is magnitude, of 2 square root of 2. Now the last thing that we're going to talk about in this video is vector operations, adding, subtracting, and then multiplying by a what we call scalar. Now, a scalar, simply put, is something that has quantity, not direction. There's a size, there's a magnitude to it, but there is not a particular direction. In a sense, it's a coefficient, right? That's the best kind of way to think about it. If you were to multiply something by a number greater than 1, you are likely enlarging that particular quantity. If you are multiplying it by something that's less than 1, you are reducing, almost like it was back in the day in our dilations, and we were talking about translations and things like that, and transformations, all those good things. And so that's ultimately what a scalar is. A scalar has only quantity or magnitude, not direction. And so what we do is when we multiply a vector by a scalar, as long as that scalar is ultimately greater than 1, then what we end up doing is enlarging it and keeping it in the same direction, okay? If we end up multiplying it by less than 1 but greater than 0, we reduce it. And then, of course, if it's negative, then it ends up flipping the direction on over. And the last thing you see on this screen here is in regards to adding vectors together. Now, I'm going to show you a quick kind of a diagram that shows two geometric representations of what happens when you add vectors together. Now, the one that I'm going to touch base more on is this part B, the parallelogram representation. What I like to do is to kind of think about this in terms of an airplane. If you have a plane, and we're going to call this V vector down here in blue an airplane. And if that airplane can go, let's just say 700 miles an hour, and then you have a somewhat of a crosswind at vector U, also having size, the speed, also having direction, which looks like it's kind of more of a north-northeast direction that it's going, obviously the plane gets impacted by the wind. And so when you take together the direction and the speed of the plane plus the direction and the speed of the wind, you get this vector addition in red in the middle. Now, I like utilizing the parallelogram representation more because I think it makes a little bit more sense. But if you have two vectors that are represented from what we call a tail to head representation, where one vector starts at the end of another, the connection between those 2 points, or the addition between those 2 points, is going from the tail of the first vector to the head of the second vector. We're also going to talk about that a little bit later on when we talk about vector subtraction as well too. So let's do a couple real quick examples in regards to the vector operations. Vector operations are really simple, all right? We are adding the x's together, we are adding the y's together, and then if we multiply by a scalar, we multiply just like the distributive property. So u plus v is simply put -1 plus 4 and 3 plus 7, and then ultimately we end up with a 3, 10. So together, u plus v, the direction of u plus the direction and size of v, together make a vector of 3, 10 that has its own new size that we could figure out and calculate the magnitude to as well. Where it says 3u, that's a scalar, so 3 represents a scalar being multiplied by a vector, so -1, 3. Just like the distributive property, we get -3, 9. So all we did really right there was we kept the direction the same, but we enlarged the size of the vector. We enlarged the magnitude of the vector there. I challenge you to go ahead and do part C on your own. The last little tidbit of this video is to touch base on what we call a unit vector. So ultimately, a unit vector is simply any vector, all right? So let me rephrase this. Any vector that's not the zero vector, aka 0, 0, has its own unit vector. So what that means is that a unit vector goes in the same direction of the original vector, but it has a length of 1. So same direction, but different size, and specifically a size of 1. And if you think about this, ultimately, if we take a vector, divide the vector by its size, but divide it by its magnitude, it's going to reduce it to a size of 1. Think about it. You take 2 divided by 2, you get 1. So we're going to take a vector, and in a sense, we're going to divide it, but really scalar multiply it by a magnitude of the vector. So it says find the unit vector of -3, 2. So we're going to go ahead and first and foremost find the magnitude of the vector, because we have to find out what we need to scalar multiply it by. So we're going to go ahead and find the magnitude, which is -3 squared plus 2 squared, and that equals the square roots. Well, 9 plus 4 is 13. So what that means is the size of vector v is square root of 13. So to find the unit vector u, we go ahead and multiply the original vector by 1 over square root of 13. And yes, this is very similar to just dividing through, but we want to think of it more as vector, a scalar multiplication. I think it will make more sense as we kind of continue on if we kind of think of it more as scalar multiplication. So ultimately, -3 over the square root of 13 and 2 over the square root of 13 is the unit vector. So once again, let me reiterate. What this means is that this is a vector in the same direction as -3, 2 that has a length of 1 instead of a length or a size or a magnitude of square root 13. All right, folks, that's a wrap for this video.